PhD advisors are the same.
Yeah.
Who is the same. One talks about hydrology, Indian monsoon, and how you can downscale, as you have seen. He goes the next step. With those downscale stuff or with whatever stuff, what can you do? Vulnerabilities, especially in the city of Mumbai, and several of you asked this question, how can this help Dharavi? He will show something about Dharavi. Okay? Vulnerabilities, urban scale. There is one work that we will probably at some point jointly start, which is working on sensors and sensing systems in urban areas, especially for prediction of rainfall, tidal surges, etc., focused on Mumbai. So, hopefully that will start, and if we start that, he'll be leading that work from here. So, the way we'll proceed is we'll have short introductions again. Keep it short, maybe your name, department maybe, and then we'll move from here. Just to give you a feel, and we have talked a little bit. Very diverse set of students from many different areas with a lot of different backgrounds and interests, but somehow all interested in climate change, the science and engineering part of it, that's one course we are teaching, and the adaptation policy side of it, that's the second course. It's a very strong mix and very much interested in what can be done. And as I was telling you earlier, we have gone through several, IIT Bombay, we've gone through several departments now. This is the penultimate one. After this, tomorrow we'll go to energy science and engineering. So before we start, we've not been able to do this with too many professors. We've had a lack, but for you, we will be able to do that as a token of our appreciation. All right. So, Shubhankar, take us through. Oh, we'll have introductions. I'm not from
So, my name is John Iacono, and I work at Northeastern. I run the University Scholars Program, of which a number of these students are.
Also to see a couple of slides which I'm going to show you. Today is actually our institute holiday, so I invited all faculty members, but they could not come. And also even get the supporting staff. So that's why I think the facilities which we have in our department, we will not be able to show you, like lab facilities and other computational facilities. I have a couple of slides which I want to show you, like 2-3 slides which will help me introduce like Center for Environmental Science and Engineering. I am working here as assistant professor from December 2007, and like this is basically an interdisciplinary institute, this interdisciplinary center, and since 1977. So we got this building in 1985. We have 12 core faculty members. Most of them are working on water and wastewater treatment technologies, and a couple of faculty members are working on air pollution control technologies. 20 faculty members collaborating from other departments, like many faculty members from energy science. They are doing collaborating research with our CSC faculty members. So we have research projects from various actually like funding agencies, like a couple of projects from Ministry of Environment and Forest. But most of the faculty members, they are having projects, they are getting funding from Ministry of Environment and Forest because their research work is more related to like water and wastewater treatment. MOE is also like Ministry of Earth Sciences. People who are working on like vulnerability and climate change, they have projects, actually project funding from MOEs. Ministry of Non-Conventional Energy Resources, as I have mentioned, a couple of faculty members, they are doing the collaborative research with energy science faculty members, and they have the project of MNES. So you can see we have around 100 graduate students, and our department, and but still they are continuing their PhD. So it's a MSc PhD dual degree program. It's almost 6 years program, and we have PhD program on environmental science and engineering. So total we have around 35 PhD students in Center for Environmental Science and Engineering. focus area, you can see aerosol and air quality group. Almost, I think 3 faculty members are involved in air quality monitoring and air quality modeling. Many faculty members are working on water and wastewater research group, environmental biotechnology group, solid waste management. Like here we have here in Mumbai city we have 3 landfills, and our faculty members are involved in that, like how to develop the treatment technologies of landfill leachate and how to control the greenhouse gas emission from the landfill. Environmental systems modeling and planning. Me and our head of the department, Professor Anil Dixit, so he is working on environmental systems modeling and planning. Environmental policy and sustainable development group. So I have heard that many students are working from Northeastern University. You have mentioned environmental policy and sustainable development group. I think 2 faculty members presently we have worked. Maybe their research interest is on environmental policy. Actually, I belong to this group, environmental systems modeling and planning. So here is a website. If you want to visit this website, the website is under construction. We are updating our website. So I think by next month, new actually website will come out. So environmental systems modeling and planning. I just want to focus on couple of principal research areas where we are developing our simulation model and we are performing optimization also on our developed management models. So couple of our students are working on river water quality control, irrigation water management, floodplain planning, optimal design of water conveyance system like pipes, and lake water quality control. So primary research challenge of this group is to develop different mechanistic model, statistical model, and optimization technique through which we can handle very scarce, unreliable observed, and uncertain projected data. In India, the main problem is quality of the data. Most of the time, you find consistency of the data is missing, a lot of missing data, and you may use very sophisticated Markov-chain Monte Carlo method to find out the missing values of the data. Still, you will not be able to capture the information hidden in the data. So because of very inconsistent, unreliable data. So so recently we have started to work with Thane Municipal Corporation, which is just the district which is adjacent to the Mumbai district. And they have this Thane city is known as the city of lakes, and there we have almost I think 35 small lakes, and we have started collecting samples from 24 lakes, and we are performing very rigorous analysis on what's the status of lake water quality in Thane city. So I have some interest on vulnerability and risk analysis. Maybe I am focusing on flood and drought, and I have developed couple of I have performed couple of analysis on urban flood and also riverian flood. So here recently we have completed one project with OECD, Organization of Economic Cooperation and Development. Here I have developed the concept of I have developed the vulnerability map, which we can club with the exposure map and with the hazard map, which will finally give you the risk value. You will be able to find out how the risk will spatially vary. Also, I have a collaborative research project with Monash University and Tata Consultancy Services. Actually, we have one MOU with Monash University and IIT Bombay. Through that, I took a research student, and fortunately, I got the opportunity to propose a topic to Tata Consultancy Services, who are actually one of the leading companies in India, and they are now supporting, they are providing the fund to us to perform the flood risk map for entire Mumbai.
So one question, if we have
MOU with Northeastern University,
Yeah.
what does it take to then translate that to actual research collaboration?
Yeah. So if we have MOU, then there are
Sorry, this is a bit unrelated.
different types of MOU.
Yeah.
Like for example, with Tata Consultancy Service, we can have like student exchange, which is possible, faculty visit or student visit. Also collaborative, like if I want to like submit a proposal to any Indian funding agency, then actually my co-PI may be from Northeastern University. So here in this frequency analysis part, I got the interest when I was doing my postdoc in University of Western Ontario, and I'm performing like multivariate parametric and non-parametric rainfall, flood, and dot frequency analysis. Anyway, like it is mainly I'm dealing with multivariate statistics. I'm not going into details because today in today's talk I will mainly focus on vulnerability and risk analysis.
So you mentioned about your postdoc work. If I may, his postdoc advisor was Professor Slobodan Simonovic, University of Western Ontario. One of those guys who does fairly unique kind of work in terms of translating climate change to intensity, duration, frequency curves in civil infrastructure. You might want to check that. Slobodan Simonovic, University of Western Ontario.
He is a very good flood modeler. Actually, when I was doing my PhD, I used to develop like optimization model, and my research interest was mainly on this uncertainty modeling, different types of uncertainty modeling, maybe stochastic, fuzzy uncertainty, or some kind of interval uncertainty, when you know like the exact value of the extreme variation, but not any distribution information. So that type of this uncertainty. But when I joined like University of Western Ontario, then Professor Slobodan Simonovic, he introduced me with flood management. Then I got I found that this topic is very interesting. I have developed my skill on hydrologic modeling, and then slowly I have started working on vulnerability and risk analysis. So we will focus on flood management. I should not say that the topic of this presentation should not be flood management. But anyway, like if you want to analyze the flood, like if you want to characterize the flood events, then we should know like hazard, vulnerability, and risk. That hazard and vulnerability, which will help us to find out the risk. So these are the major natural hazards. Like you can see, the first three, like hurricane, drought, and floods. These are hydrometeorological. It may be climatological also. The last four are geophysical, like landslide, earthquake, volcano, tsunami. But these two, distinct classes are related to each other. Like for example, in Mumbai, if there is occurrence of landslide, it may create like some I would say inundation of certain parts of Mumbai. Sometimes you may find because of high flood, the landslide may occur. So that's why hydrometeorological and geophysical, these two are related to each other. And so according to World Bank report, you can see this 2005 report, which is, and also this CREED report, it is a Center for Research on Epidemiology of Disaster, which is actually, this is a research center in Brussels University, and you can see their actually website is very well maintained, lot of data set, lot of case studies, huge reports. In this report, they have mentioned that drought and flood are particularly destructive, and they have shown that different flaws, like the economic actually damage related to drought and floods are increasing, monotonically increasing. Because of that, like World Bank in 2005, based on this report, they found that more attention should be given on drought and flood, and like drought frequency, flood frequency analysis should be performed. Different types of risk mapping should be performed so that we can quantify the drought and flood very logically, very technically. So definition of flood, like it is very difficult to define, I would say. But in general, we can define like the rising of a body of water it's overflowing onto normally dry land is flood. But this definition I am not saying is not very generic definition, because there are a number of reasons of flood. Like it may be river flood, storm surge, dam burst, flash flood, like due to heavy rainfall. Mumbai is very flood prone due to flash flood. Like Mumbai rainfall, I would say it is, you can't compare the Mumbai rainfall with any urban damage center, any other urban damage center. Okay. So because here the capturing the spatial variability of rainfall is quite difficult. Quite difficult. For example, like Santa Cruz and Colaba, the distance between Santa Cruz and Colaba is around 12 to 14 kilometers. But sometimes you will find so there is a huge spatial variability of rainfall between these two stations. As I have mentioned that we don't have very good rain gauging station, we have only two IMD operated. IMD means India Meteorological Department. IMD operated rain gauging station. One in Colaba, which is in the southern part of Mumbai, extreme southern part of Mumbai. And I would say it is western part of Mumbai. There is another station which is Santa Cruz, which is very near to the airport. So couple of actually flood events, disastrous event I thought like to tabulate, which is taken from Swiss Re report. Swiss Re is very
Tomorrow we'll have a speaker from Swiss.
And I have already read this at Swiss Re.
And he used to work at Swiss.
So actually Swiss, I read many reports from Swiss Re. I think their reports are very well documented. So actually in this report I found that there are different types of flood and occurrences also they have shown. You can see that Machu River, it is actually, it was an earthen dam which lost due to some design defect, and almost 0.15 million people were affected because of this flood. So now flood risk analysis. I thought to make this presentation very non-technical, but after that I realized that it should be technical.
Yes.
Because as I want to introduce you with flood risk analysis, so that you can acquire some interest on flood risk analysis, and in future you can continue research on developing different risk analysis schemes and applying for each of these like other hydrologic extremes. So I have gone through a couple of literature. I found that flood risk, this term, is, I would say, is very difficult to define. You see, books related on flood hydrology, you find that the definition of flood risk will vary. Sometimes you may find like the definition of hazard is different, is completely different, and it is changing from one reference to another. Exposure also, sometimes you may find that there is some confusion between exposure and vulnerability. So, but I have gone through a couple of literature, I found that if I define hazard, exposure and vulnerability, then the chance of confusion will be very less. So hazard is nothing but the threat or susceptibility of a region due to physical environment. For example, if you see like India, you will find a lot of rainfall variability. Now if you want to capture the rainfall variation, if you compare Mumbai and one of the city from Rajasthan, so Rajasthan is very dry. The soil moisture is also very less. Like the rainfall is almost, it is less than, I would say, less than 20 millimeters. Okay. So now if we pick one station from one urban center from Rajasthan region, for example Jaipur, I think you have heard the name Jaipur. Jaipur is known as the city of palace. It is a very good, very nice place, and but the weather is very extreme. So Jaipur and Mumbai, if you compare the rainfall of Jaipur and Mumbai, you will find that Mumbai is, you will find like extreme rainfall, like rainfall more than 100 millimeter per day. Like at least 2-3 events will be there per year in Mumbai. But in Jaipur, I think getting rainfall more than 10 millimeter is is at, I think once in a 10 year or 20 years you will get like rainfall more than 10 millimeter per day. So now if you want to compare the hazard of these two cities, like I would say like Mumbai has more hazard than Jaipur. So this is actually showing you this particular component will give you or quantify the threat or susceptibility of a region due to physical environment, which so we don't have any control on this hazard component. Whatever climate change is offering due to global warming, whatever the changes occurring on this hydrologic extreme, that will affect this hazard component. But the other components will change with time. But I should say that there is no direct relationship between climate change and hazard, like this climate change and exposure and vulnerability. So what is exposure? First I will define vulnerability and then exposure. Vulnerability is a measure of a region or population susceptible to damage or losses. For example, if a region is very flood prone or drought prone region, but it is completely barren land, then I would say vulnerability is zero. Because like I would say social vulnerability is zero. If there is no infrastructure, then I would say that like infrastructure vulnerability is zero. So it is actually a measure which will quantify the susceptibility of a population to damage or losses. Exposure is, I would say, it is same as of vulnerability, but the indicator of vulnerability, which may be influenced by the hydrologic parameter or hydrological parameter. For example, land use. If you change the land use, the flow through the river will also change. Okay. Also, the inundation pattern will also change. So, like exposure is a component which may be affected because of like hydrologic influences. Another example is soil type. If the soil is very permeable, then like more water will be deep percolated through the ground, and the chance of water logging will be very less. So, so once we define hazard, exposure, and vulnerability, we can just simply multiply them, and we can get the risk value. But here, the different levels of uncertainties are involved. One level of uncertainty is like how accurately you could measure like hazard, vulnerability, or exposure. There is some uncertainty, like on the measurement or quantification of hazard, vulnerability, and exposure. Another level of uncertainty is aggregation, like how will you aggregate these three. You can just simply add three components. You can multiply these three components, or you can take any other aggregation operator, like maybe you can take a maximum value of the three, you can take a minimum value of the three. So that level of uncertainty we may consider. Okay. So, so risk term itself is uncertain. Okay. So you should get the PDF of risk also. So now, if you see a very old science paper by Shubhankar, 1987, he proposed this concept like if three components of risk are represented by three circles, and you can see like this intersection of three circles are representing a spherical triangle. It's representing a spherical triangle, and the radius of these circles are representing the magnitude of these three components. If the radius of hazard is more, then automatically area under risk will be more. If the vulnerability is zero for a particular region, then automatically the radius of this circle will be zero. And if the radius of this circle is zero, then the area under risk will become zero. It will also be zero. So he has given this representation, and he has shown like if you change like one of the component of of risk, then automatically the value of the risk will differ. So here one point I would like to mention that here see, they have not considered the multiplication of these three components. Shubhankar has considered some aggregation operation through which we can combine these three components. It may be like multiplication of area or this aggregation operation. Now, to bring more clarity, I will focus on flood risk. So now hazard, like hazard analysis. First component is hazard analysis. I don't know whether you are familiar with this term flood line or not. I hope you have some idea on flood lines. So flood lines is nothing but if I ask you to draw the probability of occurrence or the exceedance probability, which will change with flood. For example, if you have a time series of flood flow, and from the time series of flood flow, you can plot the histogram, and from the histogram, you will be able to find out the exceedance probability. So exceedance probability is nothing but it is probability that the x value, x is a random value, which will exceed a particular value of the standard variable, which I have represented as small x. So this is showing you the exceedance probability, and this Ax is nothing but the CDF. So 1 minus CDF is the exceedance probability. So CDF is equal to the non-exceedance probability. Now, if you find return period is nothing but the reciprocal of exceedance probability. You can see that just reciprocal of exceedance probability is showing you the return period. Then what is the significance of return period? See, return period is nothing but expected interval between two extreme events. So, for example, if you define your extreme event as that the rainfall or the stream flow more than this small x value, if you define this threshold, x is the threshold, if the rainfall or the stream flow is more than x, then I should define that particular event as extreme event. Then expected interval between two extreme events. So remember, I'm using this term expected interval. It's not interval. It's expected interval. You should find out the interval, number of intervals from a time series, and you can find out the average of the intervals, which will give you the expected interval of the return period. Now, if you join the line of equal return period, which will give you the flood line. Once you have the flood line, that means you have defined the hazard component. Your hazard value is here.
Let me ask quickly, how many of you have heard of 100-year flood levels by now? Okay. So, are 100-year flood levels for all regions the same? But they are still 100-year. Why? What is same? Probability of those happening are the same. So, levels are not the same. So, you look at all these individual areas. This is what is said. Look at this 100-year level, that 100-year level. Basically, drop on two plots, joining all these 100-year levels, which are same 100-year levels, where 100-year levels are the same. Those are what is calling flood lines. Make sense? More or less? Thanks.
So once you have these flood lines, for example, if you have this 100 years flood line, this blue band of lines showing the 100-year flood line, and this shaded region is having the same exceedance probability, which is, for example, if it is 100 years, then exceedance probability is 1 by 100. That gives 0.01. So 0.01 is the exceedance probability of this particular region. The region shown by this blue band. Now, as I have mentioned, if you have any climate change impact component, then you can find out that how the stream flow will change due to climate change. You can project the rainfall, and you can find out, you can run any rainfall runoff model. You can find out how the runoff will vary. From runoff, you can route the runoff value, and you can calculate how the stream flow will vary. That projected stream flow, if you use, then you will be able to find out the hazard component derived from the projected stream flow. So, if you want to introduce the impact of climate change into this particular analysis, then we can easily project the flood rates by introducing or by addressing this climate change issue in hazard components. You can see, for example, if you consider the climate change, then the flood line will change its position, and this is the projected. It is showing this, the red line is showing the the flood line, considering like the climate change impact, and here the flood line, which is with the observed data set. So you can show like how due to climate change, how the flood line will change its position.
This is where? City of London?
This is City of London. City of London, actually in
London, Ontario.
Yeah.
Similovich.
Yeah.
So interesting. So if you look there, the blue line is where the flood maps were. I mean, flood line was. Right? So you could have bought a house over there, just on the left of the blue line. And then suddenly, as climate change happens, your house sort of starts to be more and more vulnerable. What that does to your flood, your house, your flood insurance, all those kind of things, that's the issue. Right? And this is City of London, Ontario. Of course, it will happen at all cities.
Yeah. So now vulnerability. So vulnerability is, as I have already defined what's vulnerability, but this is a typical method of calculating vulnerability. Like most of the time, we overlay grid on a particular region, like where I want to map the vulnerability value. Then in each and every key, we should find out we can find out the value of different indicators, like infrastructure vulnerability indicator, socio-economic vulnerability indicator, etc. So based on the literature, we can classify the vulnerability into 4 distinct classes, like physical, economic, infrastructure, and social. Like physical vulnerability, which incorporates the hazard and the exposure of a population or a structure. Like I'll give you one example of physical vulnerability. A good example of physical vulnerability is this land, this wetland. So in wetland, if you change the depth of water in wetland immediately after the rainfall and before the rainfall, if you see like the biodiversity of the wetland, you will find a lot of variation. Okay, so that's why wetland should be considered as a very vulnerable region, and we should calculate the vulnerability, which is called the physical vulnerability. Similarly, economic vulnerability, which are associated with some monetary value. Infrastructure like roads, railways, and road bridges, etc. Social vulnerability like focuses on reaction and response and the resistance of the population. And then we can find out some aggregation operation. We can aggregate all 4, maybe averaging, weighting, Pareto ranking, different aggregation techniques are there. I am not going into all this mathematical detail. Then overall vulnerability you can calculate.
So can this be used, for example, for vulnerability analysis over Dharavi versus Kulava versus Powai?
Sure. Yeah. So
and you'll show some examples?
Yeah, I'll show some examples. I have worked on
Dharavi?
Not on Dharavi city, but in Dharavi region,
Yeah.
but for entire Mumbai city.
Okay.
So here you can see I have prepared a comprehensive list of vulnerability indicators, so taken from different sources. And the example I just wanted to show you, these are few agricultural vulnerability, because Mumbai, in India, this agricultural vulnerability is very important parameter, and we should calculate that how the vulnerability due to any kind of damage in crop land will vary. So that actually we will be able to quantify to agricultural vulnerability, like percentage of arable land. It's actually one of the indicators of agricultural vulnerability. Like demography, like even POP, they have defined as population growth, urban growth, population density, age dependency ratio, etc. So these are the different demographic vulnerability indicator. One very widely used indicator is population under 6 years and population over 60 years, because evacuating these people, the population under 6 years and over 60 years is very difficult. Here also critical facilities like number of hospitals, fire stations, blood banks, number of schools. Sometimes buildings and the shelter during the time of like any extreme event. So now, once you calculate this, then we can just simply standardize, and we can show like this is more logical because this standardization technique will ensure that all the values of vulnerability indicator will be between 0 and 1, and there will be no non-negative values, and including the minimum values.
So the huge issue is to get all these detailed data
All
from
this
them.
detailed data, and like at city level it's very easy to get, not on Indian cities, but actually when I was in Ontario, I could collect the data from 6 damage centers. We call them as forward sortation areas. But actually here in Mumbai it's very difficult to get this actually set of data. Like once you have, then in some GIS platform you can just layer by layer you can keep the information, and you can just aggregate all 4 components. You will find out the overall vulnerability. I am not going into detail. There are few things like I can share a couple of papers with you if you are interested. Like case study, I will quickly show you the case study. Like this on Upper Thames over this river watershed. I got the opportunity to work on this particular watershed. And we have considered these 6 damage centers like London, Bishop, Woodstock, St. Mary's, Stafford and Ingersoll. And in London, like 17 forward sortation areas or pin code areas are there. And like we have performed some object-oriented modeling. So, and through that, we could identify like how the vulnerability will change from grid to grid. These grids are like 1 kilometer by 1 kilometer of grid. And like after this object-oriented modeling, you can combine the information, you will find out the overall vulnerability like this. And finally, our objective was to disseminate the information for different classes of people, like for general public, for decision maker, for water professionals. So, like for example, if I want to get the raw data, then being a general public, I won't be able to collect this data. So I should work as a water professional. Then only I will be able to get the access of raw data. So we have developed this web-based information system, and you can see this is very simple, actually web-based decision making tool, like web-based flood information system. And now, so we have started working on Mumbai, and we have collected like.
Sorry, one quick question. This web-based system,
Yeah.
some of the underlying data, can our students use it? Is it open? I mean, openly available?
Yeah, it is openly available. I can share with you, no problem, because this data set actually we have collected from these data set were freely available. So that's why I could manage to get the data.
But you have put it all together into some.
Yeah.
That would be great if you can share it.
Yeah.
We can maybe use it as a case study somewhere.
Sure,
So go ahead.
you can use the same data to calculate the vulnerability. Yeah, so in Mumbai, I would say Mumbai case study should be considered as a benchmark problem for any flood modeling case study. Because Mumbai, I'll explain why Mumbai case study is different from other case studies. It is a lot of influences are there, maybe tidal influence. Tidal influence is very prominent. At the same time, variability of rainfall, huge rainfall variability. Also,
Show us if you remember offhand, where is Kulava, where is Elephanta Caves, where is airport, and where are we now?
Elephanta Caves you can see.
Okay.
Airport is here. Airport is here, somewhere here.
Okay. And where are?
Yeah, and this is our IIT Kowai campus, IIT Bombay campus, and it's called the Bihar Lake, which is the main source of water in Mumbai. So
Spell it out.
Bihar Lake, BIHAR.
And all of us know the equivalent in Boston. In Boston, what is our main water source? Okay.
Kolaba region is here. It's the South Mumbai, and
We'll talk about Boston at some point, but you go ahead.
yeah. So now actually in Mumbai we have 24 words which are defined by Mumbai
Ladies and
municipal
gentlemen.
corporation.
Yeah.
And now it's known as MCG, or like this. They have defined these 24 words, and you can see the 24 words. Like we have collected couple of like vulnerability, like we have selected couple of vulnerability indicators, and as I have mentioned, like these are only few. In future, we can define more. As per the availability of the data, we can introduce new vulnerability indicators. For example, railway length at a particular grid, road length, road bridges, schools, hospitals, blood bank, all the information we have, and even the heritage building, educational institute like IIT Bombay. So we have considered IIT Bombay in this vulnerability indicator. Most of the socio-economic data we got from census data, which is freely available. Like population below poverty line, which is very important actually indicator.
How?
Like people
What
who are
is
living in,
poverty line defined?
it's very difficult. Actually, three, four criteria are there. So fulfilling people who are fulfilling those criteria, they should be considered as below poverty line. Like you can see, like we have done some crude analysis because we have completed this work in 2008, and now we found that this analysis is very crude analysis, and we can see how the vulnerability will change, spatial variation of vulnerability, considering only the infrastructural component. We overlay the grid. Grid number of grids were 510, and we found like socio-economic vulnerability. Anyway, this is just demonstrating that, and taking the census data, like we performed this analysis, and we have shown like how the vulnerability will change, socio-economic vulnerability, and you can see like the part which is thickly populated, it's showing more vulnerability. Now, this up to here I have shown you like how to map vulnerability and risk for entire Mumbai region. Recently, we got these proposals, which we are collaborating with Northeastern University also.
Yay!
So, IIT Bombay, Northeastern University, University of Maryland, and also CDAC. CDAC is this CDAC lab. They are providing the computing facility to us because running this model will take like huge amount of computational time. So these four are the collaborating institute, and we are going to develop like near real-time urban flood forecasting systems. The project goal is like urban flood forecasting using distributed rainfall, like not like design rainfall or like station level rainfall. From urban canopy coupled WRF model, it is called weather research forecasting model, and tide information. We are considering the tidal effect also, which is very important. Like when you how to combine like the rainfall extreme event and tide extreme event itself is a potential research area. So these two simultaneous occurrence of high tide and rainfall.
Major floods in Mumbai often happen when there is heavy rainfall combined with tidal effect, as we have discussed. WRF, WRF, by the way, is one way to do dynamical downscaling. We heard a lot of statistical downscaling, statistics based. This is a way to do physics based, model based downscaling.
Now background, I'm not going into detail, but anyway, like here, I just wanted to show you like few like important points, like consideration of urban canopy feedback in urban rainfall forecasting, because there are number of papers, recent research papers, which show that actually there is a direct influence of urban like urbanization with rainfall extremes, and but the present model which we are using in IITM, which is known as Indian Institute of Tropical Meteorology, they have a very high resolution weather model, and which is actually they are running this model considering this GFS output. GFS is like global forecasting system, and GFS output, it is actually 50 kilometer resolution data, rainfall, not only rainfall, other parameters also you can get. Like the lead time is around from 6 hours to 6 days. So that this GFS data like our IITM, they are using as the boundary condition, and they are running their own like this weather model to find out that rainfall value with 6 to 36 hour lead time. Okay, so we are using a similar concept, but we are going to use what and urban canopy model. They have not considered any land surface model. That means if there are two multi-story building, then how the AD will form between two multi-story building? How to consider this urban canopy is very challenging. And this IITM, they have not considered this urban canopy model, which we are going to consider in the present analysis. So hypothesis is like consideration of feedback from urban canopy improves the distributed rainfall forecasting in urban region. So this is very important hypothesis. So first we have to prove this. Distributed rainfall information improves flood modeling performance, which is quite obvious because it has. So far we are using only like design rainfall concept. Like if you have two rain gauging stations, somehow aggregate these two information, get one design rainfall to run flood model. But here we are going to use the distributed rainfall information to find out the actual inundation. And also the tide information with tide dynamic model improves inundation information in the coastal city like Mumbai. So this is the proposed plan. Like you can see like 3 different modules are here. First is short-term hydrometeorologic forecasting. This part actually we are forecasting like the distributed rainfall with 6 to 36 hour lead time. Also we have like urban flood modeling, so which is this like this purple color is showing like this urban flood modeling part, and green color is showing like tidal flood modeling. So here we have 3 different modules which will give you like near real-time flood forecasting system. I would not say it is real-time forecasting system because we have to collect the information of real-time rainfall information actually through some sensors, and we don't have like we have the sensors, but like transferring the information from the gauging station to the control station will be very difficult, and it will take some time. Like there will be 50 to 20 minutes of lag. So that's why this model we have named as near real-time flood forecasting.
It is already going into areas that no man has gone before, or woman, right? Tidal and heavy rainfall floods, and within a distributed flood forecasting.
Within a distributed flood frequency. So I have searched like many literature. I found that
in urban, that too in urban.
Yeah, that too in urban. So objective, these are few specific objectives which I have already discussed. Study area. So I wanted to spend some more time on study area, but because of lack of time, I won't be able to show like a couple of slides. You can see this is the Mithi River region. It is almost, I would say, 1/7 to 1/8 of the entire Mumbai region. And this part is very flood prone because of Mithi River. Mithi River, there is some change in slope, abrupt change in slope. The chance of sedimentation is very high. And the length of this Mithi River is around 17.84 kilometers. And total area of this catchment is 7,295 hectares. Almost 7,000 hectares. And you can see like Mithi River is flowing through like very important part of Mumbai, like Sakinaka, Saketpur, Santa Cruz Airstrip, which is very populated and industrial area. And it is going through this CST railway station also, which is a very important railway station and oldest railway station in England. So now Mithi River catchment, you can see that this part my student Sumit he has delineated in our lab. So it is showing you means two scale plot, like which is showing like you can see longitude and latitude also in exact position. Size of this Bihar Lake and Powai Lake. These two are very important lake in Mumbai. You can compare, and you can see a small blue colored dot, which is like a NEET campus. NEET campus is adjacent to IIT Bombay campus. There is a small pond, which he has shown as a small dot, and then this green color is showing the Mithi River, green color line. And this is called the Vakula Nala. You can see the dead end of this Vakula Nala, which is also like very stagnant, like very polluted. I would say tributary of Mithi River. So why should we consider Mithi River? So I have discussed with Sumit and I found like these are few reasons. Like we should, these actually these few reasons motivated us to work on Mithi River. Like slope variation, you can see very abrupt slope variation. Because of that, the siltation or sedimentation is quite abrupt. Shallow river, so very low carrying capacity, only 50 cubic meter per second. Mumbai rainfall, as I have already discussed, like Mumbai rainfall is like spatial variability of Mumbai rainfall is very high. Highly populated urban catchment, like, and also it is a mixture of industrial area and very unplanned. I would say very unplanned city, very old. So that's why like construction of any flood control structure is also very difficult. So a lot of constraints. You can see all these realistic like these problems will come when you try to implement something new. High tidal influence. You can see about 7 kilometers from Mahim Bay. Mahim Bay is the, I would say this is the outfall of Mithi River. And from Mahim Bay up to Air India complex, that means up to airport, I would say, it is almost like 7 kilometers. And there will be, you can see like tidal influence up to 7 kilometers. Illegal like sewerage lines, almost 75% human settlement even like you can see like 75% human settlement in this Mithi River region. And out of 70%, like 75%, 13% is slum area. So 13%, slum area. So that's why illegal sewerage lines are like numerous illegal sewerage lines are there. No floodgate. So there is no floodgate. Automatically, influence of like high tide is very prominent. There should be a floodgate, but construction of floodgate is also very difficult. You can't construct a new floodgate. You can see that this map also delineated in our lab. Like it is showing you the settlement, like settlement in the Mithi River. This orange color is showing the settlement. And this part is actually basically the Sanjay Gandhi National Park and 3 lakes because of this white region. This green colored dots or spots are showing like the slum area. You can see almost 13% of so 13% of total area and 18% of total settlement area.
So two questions. Where is Dharavi in the?
Dharavi is here. Dharavi is this.
And do these slums include chawls?
Yeah. Now, in photographs, you can see origin of Mithi River, which is very pristine, pure water you will get, which is nothing but the Bihar lake that just adjacent to our campus. It is around 6 kilometers from here. So you can see there is a very good dam, and which is very old dam, but still it is structurally is very stable. But immediately after that, we will find some like growth of hydrostatic or eutrophication, maybe because of pollution, but it is not because of like anthropogenic activity. Maybe some natural pollution is occurring, and which is increasing the nutrient level of Mithi River. And here also you can see like silt present in Mithi River. See that we should not call it as this river. It is red. But geological survey of India, they found like the source of Mithi River, which is very prominent. You can distinguish that this is the source of Mithi River. That's why they have defined Mithi as a river, not as a drain. Like tidal modeling is also very challenging, and Mumbai Municipal Corporation, they follow like thumb rule. Like if the rainfall is over 100 millimeters per hour and the high tide is over 4.5 meter, there can be flooding in Mumbai. So this is the thumb rule they follow. Okay, so which is very unrealistic. So as they don't have any flood modeling tool with them, through which they can confidently say like whether this is going to be a flood event or not.
So when was this? That picture that you have?
24th July 2009. So Mumbai high tide and the elevation was 5.1 meter. This is again the model detail, like how to model the tide. Not going into detail. Anyway, we are going to use like Mike flood, which is very sophisticated model. Mike 1 is mainly for the channel routing, like river channels we can route to Mike 11. Mike 21 is mainly the overland flow, like how the sheet of water will flow over the ground. And Mike urban, it is basically dealing with the drainage pattern. Like it has some inbuilt SWNM or IPANET model. I think you are well acquainted with this term IPANET. IPANET is nothing but like US like Environmental Protection Agency. They have developed a model.
EPNet.
EPNet. So EPNet and SWNM is basically for like stormwater drainage system. So you can just, these two are like inbuilt in my carbon. So all three models you can run simultaneously, and the input will be like DEM, digital elevation model or digital elevation map, like rainfall time series, tidal time series, bathymetry. That means like the elevation under the water, drainage network layout, river cross section, all the details. If you can provide, then output you will get the discharge velocity curve and also the flood evaluation and how the inundation of the entire basin will change spatially. Yeah. So now next is this the research team. You can see like CSI, like Professor Inamdar. He is very well-known geospatial scientist. Okay, so he is working in this team, and also from SIDA, this is starting. Akshara, she is involved. Professor Ganguly from Northeastern University, Manas Ranjan, he is the person who is going to deal with like the tidal component. Raghu from Maryland, he is also going to deal with like maybe the short-term weather forecasting model. Sunimal is also involved with like Professor Ganguly, Raghu, and Sunimal. They are going to take care of like this weather forecasting part, and I will be dealing with the flood modeling. Thank you very much for your attention. It's almost 7:35. So I think if you want, I can show you a 30 minutes video on methane flood. Otherwise, I can share the link with you, which is available.
Let's ask questions now. I mean, if we have a few questions, share that link with us,
Sure.
and I'll share. Yes,
Yeah.
and I'll share it with all of you guys. One thing that you may have seen is when you really get down to